Hello and welcome to this video on equilibrium. Today we're going to take a look at some things that happen in chemical systems when they reach equilibrium. So the first question might be what is equilibrium? We'll talk about that a little more distinctly in just a moment, but to get us started, it's the rate of the forward reaction or the forward process when that is equal to the rate of the reverse. And so we see an example down here that's actually from biology, and we are going to take a look at the isotonic solution. So these are different solutions that our cells can be in, and so the isotonic solution is one in which the forward and the reverse reaction rates are going to be the same. Now things are still moving, but the rate is going to be the same. And so in this case, you see that water is moving both into the cell and water is moving out of the cell, and they happen at the same rate. And so water is still moving in and out, but it's happening at the same rate. When you look at the hypertonic one, we see that most of the water is moving out, and even though there might be some moving in, the net movement is out, and the opposite is the case for the hypotonic. For our cells, we really want to be in a state of equilibrium for our homeostasis or our internal environment. If we end up in hypertonic solution, oftentimes we become dehydrated. In hypotonic, we can have cell lysis or cells splitting apart, and that's not good for us either. And so we really like to be in this state of being with our cells. Now, for some biological processes, we actually want to avoid being in equilibrium, so it really depends upon which one we're looking at. For the purposes of what we're going to look at today, we're going to really focus on what's happening chemically. And so what happens in a chemical process. So we're going to first take a look at reversible reactions. What are they? And a reversible reaction is one that the reaction goes both forward and in the reverse direction simultaneously or at the same time. And an example of this is when we take nitrogen and hydrogen gas and we combine them, we form ammonia. And we can actually take that ammonia and it can go back into the hydrogen and nitrogen gas. And because this will go in both directions simultaneously, we're going to see that this is a reversible reaction. And so you see right down here, there is a double arrow. Okay, so we have an arrow going in this direction and an arrow going back in the opposite direction. And this is representing that it's a reversible reaction. There are many reactions that actually won't reverse, a lot of our combustion reactions and things like that. But this is one that will reverse automatically. So it's spontaneously going to do both. And so that's kind of an interesting concept. All right. So what is chemical equilibrium? Well, it's when the rate of the forward reaction equals the rate of the reverse reaction, like I said before. And so the rate forward equals the rate of reverse, and the rate, remember, is going to be our speed of our reaction or the change in concentration. So if you think of the rate for these, I think of the rate as being the change in concentration per time. So the change in concentration divided by time, some unit of time. And so when that happens, we see a few different things that we can take a look at. Once we are at equilibrium, we know that the forward and reverse reactions continue. They're dynamic, and so they're continuing to happen. The reactions don't stop once they reach equilibrium, which a lot of people think they do. They actually continue to occur, but the rate of them is the same. And so because of that, there's no net change or no overall change in the concentration of reactants or products. So once they reach equilibrium, they're at this state where they're not changing the overall concentrations. The reactions are still occurring, but that's not changing. It's important to note also that the concentrations of reactants and products are usually not equal. And this is a big misconception that people have. They think if the rate's the same, then the concentrations are the same, and they're not. We actually see that the concentrations of reactants and products can be quite different, and we have a way of analyzing that. All right. So this is actually a diagram that shows us how these things are changing. And so this down here is starting with our products, and the products is the dashed line. And what we see is that the concentration, when we start a reaction, there aren't any products. We just added our reactants together. And so all the way up till this point right here, we see that this is not an equilibrium, that we're moving from our reactants towards our products. And so we're seeing an increase in our products as we go. Okay, so we see an increase in our products. We also see a decrease in our reactants. And so our reactants, as they are this reaction is beginning to occur, we're seeing that they are going to go down. And so we see that there's a decrease in our reactants. Now, at a point in time, we are going to see that the concentration per unit time, remember that's going to be our rate, is going to even out. And so we see that happen here. Okay, so now we see that there's a constant concentration. So the concentration of reactants doesn't change from this point on. And then we see that the products also do not change. So at that distinct point in time where we see the concentration of those two things no longer changes, we know that we're at equilibrium. And this is where we see the forward and the reverse reactions taking place at the same rate. So that is one way that we can actually depict this. There's some items in your book that explain what's going on with the molecules that you're going to want to read as well. Okay, so then we need to know what factors affect equilibrium. And there really are three main ones. So according to Le Chatelier's principle, stresses that upset equilibrium are as follows. The first one is concentration. And what we see with concentration is that systems shift away from increased concentration and towards decreased concentration side. So whenever you see these little brackets that we have here, these brackets are representing concentration. And for us, usually that is going to be molarity. Okay, so molarity for most of what we're doing. All right, so that's the first one. The second one is temperature. And so we see that when we have an increase in temperature, our system tends to shift away from the heat side, and vice versa. When we see a decrease in temperature, it tends to shift towards the heat side. So we'll take a look at examples of this in just a moment. And just remember that a positive delta H heat is a reactant, and a negative delta H heat is a product. And so that's our endothermic and exothermic. So we can add heat to the different sides of our chemical equation. The third thing, and I talk about these simultaneously, usually the book just talks about pressure. I like to talk about pressure and volume. So this is with gases. We see that, remember, with gases, as pressure increases, let me grab my pen here, as we increase pressure, we are going to see a decrease in volume and vice versa. And so this only has to do when we're looking at really gas reactions for our purposes. And we see that as pressure increases or volume decreases, it causes the system to shift towards the side with the fewest total number of moles of gas. Okay, so if we increase the pressure, we're going to try to kind of counteract that by then trying to decrease a little bit of that increase in pressure by shifting towards the number of moles. And so each one of these things attempts to kind of shift back more towards equilibrium when it is changed. And so these are the factors that when we make a change to these things for a system at equilibrium, there's going to be a shift in the total system to try to get back more closely to equilibrium. So how does this shift happen? Well, for a reaction, we're going to describe if the shift is towards the products or the reactant side of the equation. Sometimes people say left side versus right side. I like to distinguish whether it's products or reactants. So here is our example equation. And so we see carbon monoxide and hydrogen gas form methane and water. And we see that everything is a gas. So now we have everything as a gas. We can talk about that pressure volume thing. We also have a delta H. And we see that this delta H here is going to be a negative value. So that means that this is a negative delta H, and that is exothermic. So if that's exothermic, then we're going to add the heat to the product side, not the reactant side. So we're going to look at three different ones here. So first one is an increase in the concentration of hydrogen. So if we increase hydrogen, okay, so we're going to increase this one here. If we increase the amount of hydrogen concentration, we actually added something to this side of the reaction. And in order to shift back more towards equilibrium, it's going to shift towards the product side since this is a reactant. So since H2 is a reactant, we're going to shift towards the products. The second one that we have is an increase in temperature. And so as I said before, if you increase temperature, you're going to shift away from the heat side. So if we increase temperature, we want to shift back this direction to try to get closer back to that state of equilibrium. So since heat is a product, we are going to shift towards the reactants. I think those two are usually pretty easy for most people. The third one is usually the one that kind of gets a little bit tricky. So, and I threw us in a little loop here. So if we decrease pressure, so remember, if we increase pressure, we decrease volume. And so if we increase pressure, we're going to shift towards fewer moles of gas. So if we decrease pressure, we're going to shift towards greater amount of moles of gas. And so what I see on this side, I see 1 mole plus 3 moles. Okay, so here's my 1 mole here plus my 3 moles here. And on the other side, I have 1 mole and 1 mole. So I see that the greatest number of moles of gas are on the reactant side. And since we've decreased pressure, we actually want to increase the number of moles to kind of try to balance out that shift in pressure. So we are going to shift towards the reactants. We'll get some practice with this in class, and please ask questions because this is always kind of a thinking thing. We have to think about which way we're going. Okay. So we can place some values with equilibrium, and so we need to be able to write expressions for that and be able to calculate some constants. And so how do we put this all together? What are the equilibrium constants and expressions? So an equilibrium constant, or KEQ, and we'll give some different values in place of EQ later on, they are the numerical value for the ratio between the reactants and the products concentrations at a given temperature. So basically we look at the ratio between all of these different concentrations to find what it is at a particular temperature. So here I think that's kind of tough just verbally, but let's take a look at an example. So we're going to write an equilibrium expression for this generic equation. And so we see that the lowercase letters are going to be these are our coefficients. Oops, I didn't grab that there. So these are our coefficients, okay? Okay, and then the big ones are going to be our actual, so this one's a coefficient, or the things that we use to balance our equations, and these are representing different molecules themselves or compounds. Okay, so if we're going to find KEQ and we're going to write the expression of this, I write KEQ is equal to, and we're going to put the products on the top, okay? And so it's going to be the concentration of products over the concentration of reactants. But we have to do a couple other things with that. And so I'm going to erase this and show you what it will really look like. And so when you do that, KEQ is going to be our product. So it's going to be the concentration of compound C to the power of the coefficient, okay, so the coefficient's a little one there, times the concentration of D to the power of the coefficient of D divided by the concentration of A to the coefficient of A times the concentration of B to the coefficient of B. Now, that's a generic example, so we'll get a little more specific here in a moment. One other thing that you want to note is that where those brackets are, remember again, those are the molar concentrations, so molarity or moles per liter. And so remember that molarity is moles per liter. All right, so we want to go ahead and actually try to kind of have an idea about what happens with these values. So what does the equilibrium constant indicate? So when KEQ is less than 1, it tells us that there's more reactants than products at equilibrium. And so that tells us that we tend to favor the reactant side. When the equilibrium constant KEQ is greater than 1, there's more products than reactants at equilibrium. So we'll see that there's more products. Because remember, they're usually not the same, but every once in a while, if KEQ is equal to 1, it tells us that we have the same amount of products as reactants at equilibrium. And so that's just kind of a thing to kind of keep in mind with our different equations. Probably won't be asked a lot about that, but I think it's a good thing to kind of have in the back of our head. So let's take a look at an example of how to calculate the equilibrium constant. So the first thing that we have to do when we do these problems, it says write the equilibrium expression and calculate the equilibrium constant for this reaction. And then we have all of these different concentrations. And so one of the things to remember is that you will need to start with the equilibrium constant, whether it actually has that in the problem or not. And so for this one, KEQ is equal to, and it's going to be our reactants, and I've written it out, so I'll make sure that I have these in front of me so I don't goof it up. We are going to do the concentration of CH4. And there's no coefficient here, so it's just that concentration, times the concentration of H2S. And there is a coefficient here, so it's going to be the second power, just for the H2S, divided by the concentration of H2 to the fourth power times the concentration of CS2, and again, no coefficient, so that's it. So what I want to do is I want to plug my numbers in for that, and so we should have in the first one 0.0196 for our methane, okay, and we're going to multiply that times our 0.0329 to the second power, and we are only squaring this number here, not both of them. Okay, so square the number first, then multiply them. On the bottom, we are going to have the value for H2, which is 0.205, and that's going to be to the fourth power, Okay, do that fourth power there first before you multiply them. And then the carbon sulfide, which is going to be 0.664. Okay, multiply across the top, across the bottom, divide top by bottom, and we end up with a value of 0.0181. Each one of these had 3 sig figs to start with, so we're going to have that at the end. The interesting thing about KEQ is it does not have any units associated with it because all of our units that were in molarity ended up canceling. And so we don't represent this with because it's also a ratio. One thing to note is if you take a look at this, KEQ in this case is going to be less than 0. Okay, less than 0. And when it's less than 0, remember that that means that there are more reactants than products. Okay. One more thing here to do. So oftentimes you're given the equilibrium constant. You may be asked to determine the concentration of ions. And so how is ion concentration calculated using KEQ? And we're going to see some examples of this. So what we're doing now is laying the foundation for more specific examples later when we start to relate this to some other things with acids and bases. So what is the concentration of hydrogen iodide for this reaction if this is our equilibrium constant and we have these values for hydrogen iodine? And so when we go to do this, the first thing I do need to have is my equilibrium constant expression. And so I'm going to write that up here first. And actually, I'm going to write it right up here so that it's not down below because I'll probably run out of room. And so we are going to have our hydrogen iodide concentration on the top. And that should be squared because we have this coefficient here. So we're going to square that, divided by the concentration of H2 times I2 on the bottom. Okay, so there's our expression. We're just showing the products over the reactants raised to their stoichiometric coefficient as the exponent. Okay, so I'm going to plug all of my numbers in there, and then we're going to solve. So I have my KEQ value is 66.9. Okay. And then I have my hydrogen iodide squared on the top. That's what we want to know. Okay, this is what we don't know. And then we have concentrations for the other two. And so in this particular case, we have 0.0295. I'm going to add this in molar, my concentration value, times 0.0174 molar. Okay, so we want to get this by itself, and in order to do that, I'm going to multiply both sides by these two numbers. So if I multiply them by those two numbers, they'll cancel on the one side and be on the other. So when I rearrange this, and if you need some help with the algebra on that, please let me know and I will work with you. Okay, I'm going to keep my squared on this side, and that's going to be equal to 66.9 times 0.0295 molar times 0.0174 molar. Okay. I'm going to take the square root of both sides once I find these, and so I'm going to go ahead and square root this side so I get HI by itself, not HI squared. So I'm going to square root both sides once I do this. So in order to get this concentration of HI, we are going to find out that this is 0.0343 when we multiply each one of those together. And when I multiply molarity times molarity, I get capital M squared. And I need to take the square root of this, and when I do that, I end up with a value of 0.185, and if I take the square root of M squared, then I'm just going to have molarity. And so that's actually the concentration of our hydrogen iodide that we did not know at equilibrium. And that is all that I have for you now. We will take a look at these closer when we get back to class and do our DSNs and practice problems.